Okay.
Very good morning. Today we discuss multiple linear regression from model diagnostics point of view. This is your supplementary class to this topic, and you will know leverage points, influential points, and multiple linearity. These are important issues in multiple linear regression, and I'm sure you will find it useful and you will enjoy the lectures. Go to the next slide.
So, we will start now model diagnostics of multiple linear regression. So, under model diagnostics, what are the issues we will be covering? Leverage points, influential points, and multicollinearity. Okay. Now, you see this figure. So, it is a scatter plot between y and x, and if you see the majority of the data points, they are scattered around this ellipse, and if we consider the majority of these points or the mass of the points, then you see that this is the variability of y, this is the range where y varies, and this side this is the variability of x with respect to the mass of the data points. Now, you consider this point. Suppose your observations, one of the observations is like this. This one lies that much distance away from this center of this mass of the points, but it lies in the direction of y. You see the variability of y is this one, and it is basically much away from that y portion. But if you see this portion for the x, it is within this variability. So, outlier is a point which is necessarily related to the variable y. So, outlier is an observation which lies much away from the general mass related to y. Now, you come to the other 2 points, this point vis-a-vis this point. If you see this point, which is, if I see the variability of y, it basically belongs to this variability, that range, within this range along y, but along x, if we see, this is away from the general range of the x, and similarly the other one also, this one also. Now, leverage point is a point which lies beyond that general mass of x. So, that means outlier is necessarily related to the y related observations, and x and leverage points related to x variability, that range point of view. Now, all these observations can have influence on the regression estimates. If any observation which influence the regression estimate is known as influential observations. Okay. Generally, what will happen, you will find out that outlier will not affect the regression estimate much, but the leverage point will affect, which, for example, there is good leverage point. This good leverage point is one which is basically lying almost on the straight line. You see that if I draw a straight line here, the regression line, it is very close to the regression line, although it is out of the, far away from the general mass of the data points, but from regression point of view what is happening, it is basically lying almost on the regression line. So, it may be representing something different which will help in understanding the behavior of the system. That is why it is good. It is not distorting the regression line. But the bad leverage point is this one, what will, because of this your regression line will shift. Okay. So, by regress diagnostic in case of multiple regression, we try to find out all those influential observations including outliers, leverage points, good leverage as well as bad leverage points. Many a time what will happen, suppose one point is here, somewhere here. Okay. Apparently, it looks that there is no problem with this data, with this particular observation, but if you carefully observe the errors, you will find out that this has influence also in the regression line. So, today's discussion, we want to find out the leverages, we want to find out other influential observations, and another issue which is also very important, that one of the assumption is that independent variables, all the explanatory variables are independent in nature. So, if there is some amount of dependency between the or amongst the independent variables, what will happen? It leads to again distortion in the estimates, and that is termed as multicollinearity. So, we will find out how to identify these observations, what are the remedies to high leverages or high influential points, and what is multicollinearity, and how to detect and remedy multicollinearity. This is our example, and these are the fitted values and regression lines parameter tests. Now, see the outliers or leverages based on scatter plot. Is it visible that is there any outliers? Difficult. I think it is even the first figure, it is not clear that outlier is there or not, or residual what I can say influencing our observations. Second one, you see that sales volume vis-a-vis machine breakdown in hours. Here what happened, it is almost random, no relationship. And third one, M ratio, which we have not taken into consideration in this regression equation. This regression equation we have not considered this M ratio. We have considered x1 is the absenteeism, x2 is the breakdown hours, and if you see the regression coefficients now, that absenteeism has effect because p value is 0.022, but absenteeism case it is 0.53. So, it is that has no effect, and which is also revealed in this picture, there is no effect. So, if we include M ratio, what will happen ultimately, your regression fit will be better, R square will go to the higher side because there is almost perfect correlation in this particular case. Okay. So, by seeing scatter plot, it is not always possible to find out that whether there are outliers or leverages. So, in order to identify leverage points, you have to understand the hat matrix. Okay. So, I think we have described hat last class, not last part 1. This is the hat matrix. See, ultimately this one all related to X space. So, when you are talking about leverages, it is related to the space created by the X matrix, and this one you have already seen that this is basically H11 to H1112 to 1 in H 2 1 2 2 2n like this. I think H n1 H n2 to H nn, and there will be somewhere where H ii. Okay. So, leverage values are the diagonal elements. So, in the hat matrix, for we have I equal to 1 to n observations, and you find out the HII values. These are known as leverage values. So, H11, H22 like H n, these are all leverage values. Okay. Now, what will be the value of HII, that HII value, what will be the cutoff value for HII? That means, when we say that the observation is influential or it is basically leverage points. So, there must be a cutoff value. Now, if you see this, the distribution of the HII, you will find out that HII minus 1 by P divided by P and 1 minus HII by n minus P minus 1, this quantity follows F distribution with P n minus P minus 1 degrees of freedom. Okay. Now, if your P is greater than 10 and n minus P minus 1 greater than 50, means what we are saying, if you take large observations as well as your P is little more, and for alpha equal to 0.05, this F value is always less than equal to 2. This is we are talking about that when you talk about the multiple regression, large number of variables, large number of observation, this is the practical case. So, if this is the case, then all values will be irrespective of the P and n minus P minus 1, when this condition satisfies. So, it will be less than equal to 2. So, that what do we mean by this? When we say that whether it is influential or not, so that means you are considering a chi-square distribution and you will be considering this region, that is 0.05. So, you are saying so long it is within this side, then it is not influential. When it go to this side, this is influential observation. So, that means we want to find out HII value for this point. Okay. And it is given that, as I said, that HII minus 1 by n divided by degree of freedom and 1 minus HII divided by this is suppose this is F, this one you are finding out here. Okay. So, we want to know this, and there are several cutoffs given, but the most widely used is that cutoff for leverage point, that will be greater than 2 into P plus 1 by n, 2 into P plus 1 by n. P plus 1 is the number of parameter to be estimated or number of parameter estimated, n is the number of, that is the sample size, and this 2 is coming because we have seen that it will be less than 2 for most of the situations. So, when this condition satisfy, we say this the point is a leverage point, in the sense it has influence on the regression estimates. And what HII measures, I told you, measures the leverage values, and the sum total of HII, this will be equal to the number of parameters. So, then if all points are equally influencing, then what will happen? HI value will be equal for all the points, and that value will be P plus 1 by n. So, that means what we mean to say, that if they are equally HII equal to P plus 1 by n, when when each of the observations contributes equally, which we want also, but it is not possible always. So, as a result this distribution, and this from this distribution what we are saying, that this one for a p greater than 10, n minus p minus 1 greater than 50, if we take alpha equal to this point, this will always less than 2 irrespective of any other p when this condition satisfied. So, that is why they are saying that if you multiply this by 2, so what will happen, HII this greater than, you are multiplying by 2 into p plus 1 by n. This is the average value, this one. So, from average how much you are going this side depending on this value, that is why 2 is multiplied here. So, if your value HI value, any HI value which is more than 2 into p plus 1 by n, that is leverage value. Okay. Now, see this for our case, you see that HII values are observation 1 to observation 12 and HII values are given. These are all the diagonal values of the head matrix. Okay. Now, what will be the cutoff value? Cutoff value will be, we have now two, how many parameters we are estimating? 3. What is the your sample size n? So, p is 2 plus 1 into 2 by n, this is 0.50. Is there any value which is greater than 0.50? You see, we have not got any value here which is greater than 0.50. So, we can conclude that here is no leverage points for the problem we have undertaken. Okay. Now, this leverage point is definitely very good. It will give you the, you identify that if any observation is influential or not, but Cook has given something different also. That means, you can go by HII values and the formulation what we have discussed so far, but you can use Cook distance also, Cook's distance. What is the procedure in Cook's distance? The procedure is like this. So, I equal to 1 to I dot dot n. So, n observation are there, your y values are there and x values are there, fine. And you have used the regression equation like this, x beta plus epsilon, and using all the observations you have computed y cap equal to x beta cap. Now, what is our interest? Our interest is, we want to know is the ith observation is influencing the regression estimate or not. Now, if I belong to the general mass, then what will happen, as n is quite large, if you eliminate one observation, there will not be almost no difference in the beta estimate, because if I take n equal to 100 or 100 minus 1, that is 99, then this estimate should not be distorted. General mass. If that point does not belong to the general mass, that means it is a leverage point with respect to x, definitely we are talking about x space, then what will happen? It will affect the beta estimate. So, now what we will do, you go for another regression without the ith observation, getting me? So, if I say this one, suppose if I write this one, the ith observation is not there, y I cap, this is x beta, I can write here I, okay, let it be here only, beta I within bracket, let us give like this, that is better, parity will be there. So, what is the second equation? Second equation is, here you have taken n data points, here you have taken n minus 1 data point, the ith one, this I, the ith one is eliminated. Then what we are saying that this should not, the difference between this beta cap and minus beta cap I, this difference should not be much. Mean it should, that in effectively there should not be any difference, only rounding error, some difference will be there. Then the Cook has created one statistics, the di, which is beta cap minus beta I cap transpose x transpose x, then beta cap minus beta I cap, this divided by p into s square, and definitely I equal to 1 to n. Okay. So, he created one statistics, this type of statistics. What happened? You eliminate the ith observation, do the second round in regression modeling, find out the beta values, you have several x values, these are all matrix vector values or matrix of the order p cross p plus 1 cross 1, and then you create this type of statistics, the di equal to this one follows f distribution with p n minus p minus 1 degrees of freedom.
Sir, when we eliminate the ith observation, means x as well as y, this will not
Total observation, yes.
So, that means that this x matrix, when we consider from that matrix also we have to eliminate that.
Total, that x y total set, the ith observation including x and y you eliminate. Now, this quantity follows f distribution. Okay. So, now when what will be your say that this di, what we are trying to say, this will become as close as possible. So, we will be looking for this di value as small as possible, then we will say that it is not away from the general mass, and okay, fine. So, as a result what happened, using this, now can you not find out that what will be the influential observation? It all depends on that where you want to put the cutoff value, depending on the f distribution you will be able to do. Now, question is, there are suppose 1000 data points. So, should I go for that 1000 plus 1, and every time you are eliminating one, the first one, second one, like this, so many observations. So, you will be having so many regression fittings, regression equation you have to develop, you have to calculate beta, that beta I equal to 1 to n. Okay. But it is not like this, you do not require to do this several times. There is the way out is that di is Ri by p Hii by 1 minus Hii. So, Hii is this, these are the basically the diagonal elements of the hat matrix, this is known, p is known. Then what is Ri? Ri is basically Ei by square root of s square 1 minus Hii. Ei is the basically the error one. So, you can write like this, epsilon I cap. You know s square is SSE by n minus p minus 1. So, that means when you are fitting one regression equation, you are getting everything. Now, put this value Ri value here and find out this value, and then you say whether it is what I can say, what is the distance, you measure the distance and using F distribution you find out. Now, the cutoff value, what it says that the cutoff value is given that if di greater than 1, then it is basically significant. This is Cook has given this, that for di greater than 1, the observation having this, that will be significant. Okay. Now, we will say what is the procedure. Procedure is, first you find out the Cook's distance using the formulation. That formulation will be this one, you will be using this, use this, find out the Cook distance. Yes, not coming. So, using this you find the Cook distance. So, ultimately 1, 2, then n, then di value you are getting. So, if I say d1, d2 like this dn, then you find out the maximum one, which one is maximum, let the di, this one is the maximum distance. Correct. So, for this maximum distance, what we say, that di follows fp n minus p minus 1. So, I will take the maximum distance and then what is p value in our case? In our case, p is 2, n minus p minus 1 is 9, and then I have taken 0.25, not 0.05. Even when I have taken 0.25, this value is 1.62, that but our d10 value is 0.52 only. So, it is much closer. If I see the F distribution table, graph like this, we have taken 25%, this is 25% and this value is 1.62, but your maximum value here it is 0.52. So, it is not at all a influential point. Okay. Then we will go for multicollinearity. Okay. Now, multicollinearity, as I told you, that multicollinearity is a issue where independent variables are not truly independent. There is dependent structure amongst the independent variables, and under such condition what will happen, if there is perfectly linear case, linear dependence case, that determinant of this x transpose x will you will not get, it will become 0 and ultimately inverse you cannot create and you will not get the estimate values. So, multicollinearity has to be tested, and multicollinearity can be tested through 4 different procedures, and these are known as variance inflation factor, tolerance statistics, eigenvalue structure and multicollinearity condition number. Okay. So, what we will discuss? We will first discuss the variance inflation factor. Okay. What is variance inflation factor? Variance inflation factor is something, suppose we are talking about that out of these p independent variables, there is correlated structure in the sense dependence relationship. So, arbitrarily we are taking one independent variable as dependent variable. We are not considering y here, we are considering only the independent variables. Then we are taking one of the independent variable as dependent variable and all other independent variables as independent as influencing that independent variable. So, x j is now affected by x1, x2, xp. Okay. Then you are making a regression equation. So, your regression equation is now x j is beta 0, beta 1, x 1. So, like this beta p xp plus epsilon. This does not include xj and y. Okay. Then you find out the rj square. So, that will be SS rj by SST, that is for the jth variable. So, then you create variance inflation factor equal to 1 by 1 minus rj square. For example, in our case absenteeism and machine breakdowns, the beta values are this and variance inflation factor is 1.092, both cases 1.092. So, if rj is 0, if rj is 0, then VIF will be equal to 1, and we do not want rj apart from value either apart from 0 value, we want this 0 value, that is the best value, because rj 0 means no correlation.
No regression is not valid. RJ is 0 means there.
Regression, that means xj is not dependent on the other independent variable. So, you have to create this type of variance inflation factors for each of the variables. Then you see this here, what happened, your r square rj square, this rj square 0 mean VIF 1, if it is 0.2, 1.2, like this. Okay. Then there is another concept called tolerance. Tolerance is nothing but just reverse. Tolerance is 1 by variance inflation factor. So, if you use tolerance or variance inflation factor, they are both are same. Ultimately, here what is happening, you are getting within a 0 to 1 scale, 0 to 1 scale. Here any value is possible. So, as if we get in terms of 0 to 1 scale, it is easier for us to interpret. Okay. So, now then what will be the VIF value that should we consider? You are getting me? For basically we say if the VIF value is 10 or more, this means high collinearity, high relationship. So, 10 or more, 10 is the cutoff value, it should not be 10 or more. 5 also, 5 is the warning limit, you can think of. So, that means if tolerance is 0.1 or less, or variance inflation factor 10 or more, that is not desirable, but when if it is 5, and then it is warning case. Then another issue is that another is the eigenvalue criteria. What is this eigenvalue criteria? In eigenvalue criteria, so all of you know that the correlation matrix we are talking about correlation matrix of X n cross P, which will be okay. So, this is P cross P matrix. Now, using spectral decomposition, this R can be written like this, that I can write that Vj lambda j Vj transpose j equal to 1 to P, where lambda j is the jth eigenvalue and Vj is the jth eigenvector. Okay. So, you can any this P cross P matrix, this matrix can be decomposed into its eigenvalue and eigenvector components, and this can be that means if I know eigenvalues and eigenvector, I can reconstruct R, because this one is P cross 1, this one is 1 cross 1, this one is 1 cross P. So, if you multiply these two, ultimately P cross P matrix you will be able to recreate. Now, what is the meaning of this eigenvalue here? When you do the spectral decomposition eigenvalue here, this is something like this. So, you consider two variable case, suppose x1, x2, x1. If they are dependent, you may get a structure like this. For the perfect dependent case will be like this. Okay. So, here R 1 2 equal to 1. So, what we mean to say here, that we do not require x 1 and x 2 to measure. If we transform the axis by certain degree, this theta degree, then what will happen? You will get another dimension which will capture the totality of the data given here. Now, so that means if I can do some manipulation here, transformation, so you rotate this x 1 and x 2 by theta, you are coming to this place, and here this axis is having the variability from here to here. This variability is captured by lambda, and the direction is captured by. Okay. So, what we mean to say? We are trying to say here that only one dimension is required. If the structure is like this, only one dimension is required to measure this, and that one will be lambda 1 and then V 1. So, lambda 1 V 1 is sufficient enough to capture this data, because if I go in along this line, my variability here is this, but what is my variability along perpendicular to this line? 0. So, lambda represents the variance component. So, if my structure is like this, then lambda 1 and I have taken two variables which in the standardized case, so this is 1 and this is 1. So, then the both the variability 1 1 is captured by this. So, this will become 2, because the total variability is 2 here for the two variables. So, other dimension there will be 0. So, what will happen? Lambda 2 will become 0. So, in the two variable situation, when you decompose the R matrix into its eigenvalue eigenvector, and if you find out that one of them is 0, lambda value is 0, then it is a perfect correlation case. So, similarly, if there are p such variables, so you will be getting lambda 1 greater than equal to lambda 2 greater than equal to lambda p. This way you extract. So, the first component will have the maximum followed by like this. So, it may so happen that when the R is basically it is basically P cross P. So, we assume that R or S or X transpose X, when we do regression, we assume that X transpose X is full rank. Now, what will happen if you find out that out of this P lambda eigenvalues, suppose lambda 1, lambda 2, lambda m, these are basically having values not equal to 0, but m p plus 1 to m p, these are close to 0. Close to 0. So, what will happen in that case? Basically, rank deficient, that means this is not full rank, and these 0 are representing that there are large number of, if m plus 1 to p, that large number of independent variables, so called they are not independent. So, there is multicollinearity. This is what is known as eigenvalue criteria. So, that you take the R, that is the correlation matrix, go for your spectral decomposition, that means eigenvalue eigenvector decomposition, then find out the eigenvalues. If you find out that some of the eigenvalues are close to 0, it simply indicates that your case is not independent, the independent variables are not truly independent. Okay. Then there is one is multicollinearity number. This multicollinearity number is known as MCN, which is basically the largest eigenvalue divided by the smallest one. And now, if there are many values close to 0, then definitely this lambda p, this one is very close to 0 and it will be a very high value. MCN will be a very high value. So, if MCN greater less than 100, it is not a serious multicollinearity problem, not serious, but if it is greater than 1000, it is a serious issue. Getting me? Then there is one relationship from the MCN and VIM point of view, that VI various inflation factor, it is AM less than MCN less than sum total of this VIFM is the maximum variance inflation factor, it should be less than this, less than P into J equal to all the sum of all the variance inflation factor. Now, can you not find out the data for data whatever we have given here, we have seen here, this one, if it is asked to you that you find out that whether multicollinearity problem is there or not. So, what way you proceed? What will be your case? For example, 9, 62, 8, 58 and then 7, 64. Suppose these 3 data points are given to you. Okay, so, this is my x, this is 3 cross 2, this is x1 and x2. What is our aim? We want to test that x1, x2, that multicollinearity issues are there or not. One is that you find out the regression, you regress x2 on x1, there are only 2 variables x2 and x1 is enough, and then find out the VIF. Other one is, I said that can you not find out the R value? How do you compute R here? What you require to do? I told you in probably multivariate descriptive statistics class. I told you, you first find out R. R, I told you that x tilde transpose x tilde 1 by n minus 1, and your x tilde is, suppose if I say x tilde is something like this, yes. So, suppose x I j tilde is there, then x I j tilde will be x I j minus x j bar by standard deviation of this. So, we require to get R square value, R value first here. Once you get R value, suppose for example, let R value is, I am giving some arbitrary value here. Suppose R value it is 1 and this is 1, and let us take 0.8 here, although it is not like this, 0.8 here. So, you got the R value. So, what is required to do? You require to find out the eigenvalues. How do you find out eigenvalues? Normal process, that characteristic root characteristic. So, you have to first consider that 1 minus lambda 0.8, 0.8, 1 minus lambda, this determinant, this equal to 0. Let us see this, what will happen here. Will we get 1 minus lambda square minus 8 square equal to 0. So, 1 plus lambda square minus 2 lambda minus 0.64, it is okay. This equal to 0, then lambda square minus 2 lambda plus 0.36 equal to 0. Then there are two roots. So, lambda will be minus b means plus 2 plus minus root over b square means 4 minus 2 into 0.36 divided by 2 into 1 into 1, this is the case. So, then plus 2 plus minus root over 4 minus 2 72 na 0.72 by 2. So, 2 plus minus root over 3.28 divided by 2. So, 3.28, what will be the square root? So, see, if it is 12, then 144, if it is 14, 190, no, it will not be not 12, it is 328. I think 2 point around 1 point something, if it will it be 2? 2 into 2 is 4, it cannot be. So, it will be less than 2. For example, 2 plus minus maybe it will be 1.8 by 2. Then it is 3.8 by 2, 1, this is 1.9, another one is 0.2 by 2, 0.1. So, we can say that it is basically, it is a multicollinearity problem, because we have already taken this. So, essentially then what is coming now, that multicollinearity issue can also be tested using the R matrix. So, if any, what will be the value of this correlation coefficient, and which will tell you that yes, there is multicollinearity. Definitely with the two variable case, when 0.8 it is saying that it is almost that multicollinearity factors is like this. Now, what is our MCN multicollinearity number, that lambda 1 by lambda 2. So, our 1.9 by 0.1, this is 190 or 19, this is 19, this is 19. So, what we have seen that multicollinearity number less than 100 is not a serious issue. That is what is given there. If multicollinearity number is greater than 1000, that is a serious issue. So, then what you will do? Will I go by this logic, or as I am able to see that there is 0.8 and one of the this 1.9, this one of the dimensions, the variability explained is much higher, second one is much lower. So, should I go for regression, or we will simply dimension, we reduce the dimension and then we will go for regression? What will be your issue? Basically, see, if I go, actually although 0.1 and here we are getting 0.9, because of this two variable case, I think this 0.8 is not at all a simple issue. I think we should not go by this. That is what I personally feel using the data analysis by this logic here now. This 0.8 is it's a reasonable correlation coefficient.
We can perform
Dimension reduction, it is better.
This range is given in the
This is given by researchers, statisticians. Okay. Then see, then what we will do, suppose here it is p two variable case, but there are p variables, suppose p is get 15 variables or 20 variables. So, under this case you will be having a big correlation matrix, and using this correlation matrix, the seeing this value you cannot judge, because even in the two variable case, if I see 0.8 and then I discard, but from multicollinearity number point of view, it is saying that you should go for regression without bothering about multicollinearity. So, you cannot judge just by seeing the R matrix. Fine. Then the solutions are, what are the solutions? Solution is, one is the principal component analysis when there is multicollinearity. So, principal component regression you can go for. So, principal component regression, that means you reduce the dimension as you were saying, then find out the what are the lambda values that are significant values, and only those components you take. Then you y is for those component, you find out the regression line. So, beta 0, suppose beta 1 PC1 plus beta 2 PC2 plus like this beta p PCP and so on. PCP will not go, we will go for beta m PCM. P is the number of variables, where m definitely is less than equal to p. Now, if you go for PCA, what will be the problem? Problem is that now your original variables are missed. So, then, but you may be interested, no, I will not do like this, I want to keep the structure. Regression equation structure is like this, x1 and x2, this is the structure xp, x0. Now, what happened? They are dependent. Suppose this is dependent with this. So, okay, this is dependent. So, what do you want? If you go by PCA, this structure will lose, this independent variable, original variable will lose. So, you may be interested to that first you find out of these many variables, what are the independent variables, what are the dependent variables, strict sense. If you still find that no, these are still independent variable, they cannot be treated as dependent variable, then you can allow them in modeling, you can allow them to covary. In the sense, I will do like this only. In a regression, you are doing this, but here you can allow the covariant structure to be getting me. So, you do not go for transformation, you will simply allow the covariant structure to be kept as it is, then estimate. This estimation is also possible. This estimation will be understanding through path model or path analysis. Okay. So, then remedy to multicollinearity, what we have discussed, remedy to multicollinearity, one is the transform the data, transform x, that is usually we go for PCA. Here PCA is possible only if your interest is prediction, because you do not bother about the original data is transformed to what scale and whatever these things, but we want to predict, then fine. In electrical engineering, I know that some of that predictions using PSP, that is principal component regression, it is done. If you want to keep the independent variable,
the name of the variable
same, and you don't want to lose the nature of the variables, then you go for path analysis. This path analysis, what it will do? It will estimate same regression parameters, this regression parameters, but it will allow the independent variable to covary amongst them. This covariant structure will be taken into consideration, and then these two analysis it is better to go for path analysis when variable explanation is an important issue. Variables contribution in explaining the why is important. Okay. So, I think we can stop now.